So I'm going to talk about our work that we've been doing the last few years on a method known as neural radiance fields for view synthesis and beyond. The goal is to enable virtual experiences of real-world scenes. You want a user to be able to quickly click a few images with their phone. And you have these input images that look something like this. And thereafter, you want to enable an immersive visualization, something that could be used in virtual and augmented reality. Now, you notice here that I'm capturing the reflections on the puddle, the highlights from the bike, and something like this enables you to promote your traditional 2D images into 3D photography, to be used in a kind of immersive experience, to be able to visualize objects for applications like photography, for e-commerce, avatars, so many things. More formally, this is known as view synthesis, where you take these input images of a scene, and thereafter you have some kind of scene representation, and you want to be able to create novel views from new viewpoints so that you can fly around the scene, have a full 3D representation. Now, what does this lead to? Using lots of compute. Okay, that's the common theme throughout this national research platform. It is actually kind of interesting because when I got to UCSD and my previous background was all about very core mathematical, classical signal processing ways of modeling scene representations, modeling appearance. And in fact, when the first call for the NSF JSCI came out, and Tom and Larry spoke to me about that. I mean, we had just begun. My first paper in machine learning was 2016, December, actually. And I didn't really predict that we would be here today, okay? But such is how the world has evolved. Now, we use a number of different machine learning algorithms, multi-layer perceptrons that I'll show you in a moment, but also convolutional neural networks, transformers, diffusion models, either specifically on a single scene for view synthesis or multiple scenes, and of course, many other research problems we deal with. We also spend a lot of time on generating synthetic, in some cases large-scale synthetic data sets using computer graphics rendering that doesn't always run on the GPU. And that is the primary reason for these spikes in CPU hours we see more than any other user of the NRP. All right, going back to view synthesis, this is actually a problem that has at least a 3-decade history, and that's why it's really exciting to use modern machine learning methods and the resources of the National Research Platform to really make a big advance in this area. So in 1993, Chen and Williams had this paper at SIGGRAPH on view interpolation for image synthesis, which curiously enough ended up in both volumes of seminal graphics papers for the first 25 and the next 25 years. And essentially, they introduced the problem. It was entirely for synthetic scenes. These are images from 93, not something you would put up today, but nevertheless had a very large impact. And probably the biggest influence in terms of the theoretical foundations is this paper on light field rendering from my advisor Pat Hanrahan, Mark Lavoie from SIGGRAPH 96, that shows the basic idea of why this is possible in the first place. If you take a number of images around an object or a scene, you can, of course, interpolate the individual images, but you can go beyond that, and you can look at a point which is moving towards the scene. Now this, something like this. Okay, never mind. So you can resample and combine the rays from the individual cameras. So this enables you to get an idea of how, with the right kind of scene representation, you can take these images and create a three-dimensional representation of the scene. Most of these works were still using, until about 2020, relatively simple geometric descriptions of the scene or particular things known as disparity maps. How much does the scene move between two adjacent images? Our work on neural radiance fields from 2020 introduced fundamentally new descriptions in terms of a volumetric representation of the scene and predicting these volume densities and colors using machine learning with a multi-layer perceptron. I'm going to show you a short video of that now. Hopefully audio works.
We present neural radiance fields, or NeRF, a new method for representing complex scenes that achieves state-of-the-art results for view synthesis. Given a set of input images of a scene, which in this visualization is a Lego bulldozer, we optimize a volumetric representation as a continuous function which is defined for any 5D coordinate, consisting of a location and view direction. We parameterize the scene representation as a fully connected deep network that takes in a single 5D coordinate and outputs the corresponding volume density and view-dependent emitted RGB radiance at that location. We then use techniques from traditional volume rendering to composite these values along a camera array to render that pixel's color. Since the rendering process is fully differentiable, we are able to optimize the scene representation by minimizing the error of rendering all camera arrays from a collection of standard RGB images. Our method is able to reconstruct high-quality novel views from a sparse set of input images of a scene. Our strategy outperforms prior work that also represents a scene within the weights of an MLP, as well as prior work that represents a scene as a set of multiplane images, or as a discrete voxel grid. Here, we visualize additional results across a wide variety of real-world scenes, each captured with 20 to 80 input images. Our neural radiance fields are able to render photorealistic novel views of scenes, with fine geometric details and realistic view-dependent effects. We're able to capture all of this visual complexity in just the weights of a simple, fully connected network, requiring only 5 megabytes of storage for each scene. We can visualize the detailed view-dependent effects captured by our representation, such as the sharp reflections and specularities on this car, and the glossiness of this room's television and conference table. Our representation captures high-quality scene geometry, such as the details on this red flower, and complex occlusion effects in these tree leaves and ornaments. We present.
All right, now neural radiance fields has really led to a revolution in the ability to take images, create representations of the scenes, and it has had wide impact in practice. I mean, I actually have to thank Larry for giving me this slide from the information I supplied to him. So you see that the New York Times is using it to generate workflows for portraits. Mark Zuckerberg mentioned it in one of the Meta keynotes for 3D object scanning. Time magazine listed a subsequent work which made it really fast that I'll show in a moment as one of the top 200 inventions in 2022. And so in a number of different applications, these techniques are being used. Here is work that Thomas Mueller and colleagues from NVIDIA did in 2022, where they were significantly able to reduce the compute. And in real time, you can see the scenes training and rendering. And more recently, there was this work on 3D Gaussian splatting that produces even higher quality and faster results, including for these complex kinds of environments, outdoor environments that can, after a period of training and optimization, be rendered in real time. Now, how can these kinds of techniques be used in terms of practical applications? And I'm just going to show you a selection of a few things that people have done. Here is an example of using neural radiance fields for digital twins, where you can take your entire showroom or your entire factory, and you can produce this three-dimensional representation that you can view from different viewpoints and create this very realistic digital twin. Moreover, with the tools we now have available, ordinary users can actually capture these kinds of neural radiance fields. And this is from postings on Twitter, actually, where you're using neural radiance fields for landscapes. Presumably, the source images were taken from a drone. But after you have done that, you can create these kinds of beautiful shots of the entire landscape from the sky. And of course, I want to make an example with my pet. Since it is a volume, of course, this is hallucinated inside the volume, but you can actually even zoom in to your pet. And you can see these kinds of furry objects are not a limitation for the method. Nowadays, of course, there is a lot of interest in large language models, things like ChatGPT. In fact, you can couple these large language models to neural radiance fields. They, in fact, provide a bridge between text-based generation of imagery, for which you have a lot of data on the internet, and three-dimensional models, where you have much less data. And therefore, they allow you to use the power of the National Research Platform, machine learning, to be able to create generative AI for 3D. Here is an example. This is not my own work, but this is work from colleagues at Berkeley, where they use language models to edit a neural radiance field, where you can just use your language editing and do these kinds of edits on your scene. And that gives you some kind of a hint on the future in terms of extending large language models to also operate not just on text, but two-dimensional images they already do, but in this way on entire three-dimensional virtual representations and virtual scenes. Now, the students who worked on this have subsequently gone on to positions at Google and as well as a startup, Luma AI, where you can, in the mobile world, you can take a bunch of images with a camera, with your mobile phone, as I showed you in the first example, and create neural radiance fields. Within the context of Google Street View, these techniques are now used to be able to create photorealistic renderings, including of interiors. I just want to play you the video. Okay. We seem to have lost audio. I don't know why we've lost audio here. Pardon? Yeah, so...
be busy, so you have all the information you need to confidently make a decision about when and where to go. If you're looking for a bite to eat nearby, you can explore all of the eateries in the neighborhood. You can even glide down to the street level to explore restaurants and peek inside to understand their vibe before you book your reservation. This stunning, photorealistic indoor view is powered by Google's Neural Radiance Field, or NeRF as we call it. With NeRF, we use 2D images to generate a highly accurate 3D representation that models the true complexity of what a place is like. To transform ordinary pictures into stunning 3D models, our artificial intelligence seamlessly predicts where different colors should be applied in space, so you can see if a restaurant has an awesome outdoor patio or a great bar area.
All right.
If you're considering a visit, you can virtually soar over the building, find the entrances, and get a sense of what's in the area. If you're considering a visit...
All right. All right, so, and so one of the other things we have been applying it to recently has been in creating avatars. That is a topic of great interest. So what can you do with faces? What can you do with your faces in virtual reality for 3D video conferencing? And this is work I did with my PhD student, Alex Trevethick, Manmohan Chandrakar, collaborators at NVIDIA, where from a single input image, you can create this kind of radiance field in real time, just from a single input image from an iPhone camera, from a video stream, processing each image independently. And thereafter, you can change the viewpoint. You can even create a representation that's used for video conferencing. And let me just show you the video. Yeah. So this is all happening in real time. You're just seeing the single iPhone is being used to capture. And you're able to take the input, create these outputs, create output depths. And it is robust if the person puts on headphones or has glasses, etc. And it can even be applied on babies, as well as later we'll see that it can be applied on paintings as well. So it generalizes very well. So here you're applying it on your doll. And in this case, you can apply it on paintings. Again, these representations provide a bridge from 2D to 3D. So if you can apply it on individual images and paintings, then you can do things like this, where you take a text-based avatar, which would be a 2D image, apply our representation, and now suddenly you've taken language-to-text models and you have been able to extend them to 3D. It can also be used in the context of 3D video conferencing. This was a booth that was set up last year at the SIGGRAPH Emerging Technologies, where you can take this radiance field representation and actually represent it in something known as a light field display, which provides different views from different viewing angles. And that points towards the next generation of 3D video conferencing. The Intelligence Advanced Research Projects Agency has introduced this REBA program to essentially apply neural radiance fields on large-scale images and large-scale environments, where you want to be able to take a few images from different altitudes, varying altitudes as part of the name of the program, and thereafter you want to be able to navigate and create a photorealistic model for the rendering. This is, again, a large user of computation, and my student, Kaiwen Jiang, who's working on this, you can just read his text about the benefits of the National Research Platform. I want to mention a couple of compute resources we have added to the NRP cluster. So in 2018, we had a large ONR DIOREPA board of 500K, which added more than 25 8-GPU nodes. That was our first major purchase in terms of computational resources that we've added to the cluster. And it also included a couple of compute nodes for the CPU-intensive synthetic rendering. If you looked at the plot earlier, you saw the large spikes there. More recently, from the Center for Visual Computing, of which I'm the director, we used funds from that to buy a 100K storage server, and add that to the NRP resources. It's now completely integrated and can be used in the resources, because many of the data sets we are seeing now are really exploding in size and we need better storage. The AI algorithms that we've used recently are the classical neural radiance fields and fitting from single or multiple images with multi-layer perceptrons. But we also work on generalizable nerve models, which is a computationally heavier task where ultimately at inference it may be easier, but you want to be able to learn across a range of different models so that you don't have to optimize for each model separately. And that has used methods like transformers. We have looked at scene generation with diffusion models. I showed some simple examples earlier, but we've also done more advanced work recently. And Gaussian splatting is one of the newer methods for radiance fields with parameters controlled by convolutional neural networks, so you can handle different times of day within the REBA project. We've also developed new methods to train generative adversarial networks using various triplane type nerve representations. Just listing some of the recent publications in this area. And as you can note, a couple of best paper awards at ECCV, as well as the ACM dissertation honorable mention to the students involved in the original neural radiance field paper. And I was excited, actually traveled to Beijing last year for the inaugural Frontiers of Science Award for this work. So to close, I just want to acknowledge the students. Before we worked on neural radiance fields, we had a number of papers and light field cameras, and want to acknowledge the students there and the collaborators, as well as the funding agencies. And of course, Larry, Tom, and the crew, the support at the San Diego Supercomputing Center for the National Research Platform that has made this and other research efforts actually feasible. All right, thank you very much.
All right, do we have any questions?
You are probably aware that phones can also do 3D scanning and so on. Mm-hmm. So somehow I'm a bit puzzled why you need huge amounts of GPU time, probably because you start with photos and not with LiDAR and photos.
All right.
But these phones can do similar things.
So, a couple of different answers to that. So first place, if you have multimodal data where you have images as well as 3D, that can be included and you can get better results. But in many cases, we find that just using the RGB information is adequate. And in fact, one of the algorithmic innovations in neural radiance fields is not to use a representation, a traditional representation of depth or a mesh or a disparity, because those representations actually are fairly error prone. And therefore, we optimize a new volumetric representation. So for many problems in view synthesis, you're better off just core looking at the RGB images. There might be other cases where the depth sensor benefits you. The second question is in terms of computation. So there are certainly neural radiance fields algorithms such as instant NGP or even Gaussian splatting that are designed for a given scene to run very efficiently on your desktop GPU. And in fact, I showed some of the examples with nearly real-time results. However, there are a bunch of other research problems where we need a lot more computation. So for example, like in the Riva data, where they have very large-scale environments, and you may also be trying to analyze the variation across different times of day in sort of different seasons and so on. Or in cases where I showed some of the language model work where you are using diffusion models to be able to generate general scenes, for example. And some of the work where you are being able to generalize across multiple scenes. And so there's a range of problems, some of which you can do very efficiently on a single desktop GPU, and some of which require the full power of the platform. Also, often we need to create synthetic data sets, and that requires a huge amount of computation. Yeah.
So I have seeing this really striking work, is there still a role for classification and or memory? Namely, as you generate these models, even within the efficient algorithms, if you can begin, like a human being, to recognize certain attributes, then you can further accelerate it. And then also, for every model that you generate, can you store it or store a representation or a reduced representation so that then later you have an improving knowledge of the algorithms to regenerate higher fidelity images.
So, one of the interesting things which I didn't fully cover in the talk, so I showed it for portraits, but one of the things we worked on last year is generating these NeRF representations in 3D scenes from a single image. So for a portrait, there is a lot of previous information about human faces. And in fact, the data set was created entirely from a GAN model, no synthetic image generation, no acquisition on a light stage. You generate 16 million images from a GAN model and you train the data set. For general objects, now that we have these kind of general 5 billion element diffusion models, etc., we've seen a remarkable advance in progress that you can look at a single image of a general object, and essentially by doing classification, because you kind of know what it is, and having that prior information, you can create a full 360-degree flow around it. Now, there is the next step of it that so far we have not had large-scale data sets in 3D and large-scale neural radiance field data sets. But a startup like Luma AI, where one of the students, Matt Tanchik, is working, now people have taken nerves and are uploading there. So now they have 1 million nerves, right? So they can then do machine learning on this, and you can imagine ways of making further progress, as well as storing it with kind of a latent vector that generates a full range of models. Yeah.
So having said that, then thinking again about human intelligence, the next step would be interactions. Once you classify objects, scenes, objects in a very general sense, you can then generate knowledge about how they interact.
Yes, and so some of the work now deals with physical simulation, right? So not just that you want to go around the object, but you want to place them in real scenes, and you want them to be able to interact with real scenes. And that can, again, I mean, you can try to estimate not just the color of the object, but also the physical properties and the way it interacts with the scene. Yeah.
Thanks, great talk. You've seen it, you showed a great example of semantic mapping. What would it take for, scientific instrument data like microscopes, LiDAR, to be using these techniques with the mapping?
Yeah, so I think there is definitely a large scope for that. And in fact, the field of tomography is essentially recovering a volumetric representation. And in fact, some of the neural implicit representations that have been used in neural radiance fields have been and can be used in tomography, even for things like black holes reconstruction. I mean, people have been using these neural implicit functions, which of course Larry is the black hole king here. But the idea of general volumetric representations and neural implicit representations of them has broad impact, even in the scientific domain.
One more short question.
Oh, yeah. Thank you so much for your super impressive presentation. Just a quick question in terms of the resolution.
Yes.
Because my background is the manufacturing, right? For example, if we take the picture on the objects for mechanical, for example, for 3D printing, what's the best resolution you can achieve? And then you can convert to like 3D, and then we can use 3D printing to fabricate.
So one of the technical innovations, of course, I mean, this talk is for a general audience, so I don't go very deep into the technical advances. But one of the key technical advances in neural radiance fields is this notion of positional encoding. And what that is essentially the multilayer perceptron is taking the spatial location and the angular coordinates and it's outputting a color. But if you just do that naively, you will get a very coarse result. So you effectively encode essentially a Fourier series with powers of 2 increasing Fourier coefficients. And once you give that as input, you are able to recover a much higher frequency output. And one of the things we compare it to is using a sort of grid at some resolution like 256 cubed. And this produces a higher resolution than that, right? And so in general, these methods do produce fairly high resolution. Of course, measuring it because they are neural methods, so measuring it as a conventional grid resolution is not always a trivial thing to do that mapping, right? Because they actually have more capability of producing higher frequency detail. Yeah.
Thank you.
All right. Thank you very much.
All right. Thank you.